First of all, I thank the organizers for inviting me to talk here. And secondly, maybe most importantly, I thank them for organizing this wonderful meeting in this beautiful place. Okay. Okay, this is the title, so I will start to try to explain something about the title. I will be a little bit sloppy because there are a lot of things, and sometimes some things are mathematically well understood, something not, but at the end, the result I'm going to present are clearly mathematical statements. So they comes from some heuristic, which is still not well understood, in my opinion. Okay. So you start immediately from something terrible. So there is a notion, of course, of partition function in quantum field theory, essentially in Euclidean quantum field theory. Say, I'm focusing on two-dimensional conformal field theories. So you have fields on some space-time, and here space-time is meant to be a Riemann surface. Okay. In order to define this trick, even formally, what is needed is some metric or some conformal structure on this Riemann surface. And of course, you have to deal with the definition of the functional integral, which is non-trivial, and I would say it's not completely understood. Okay, but the point here is to make this for all genus Riemann surface. There is a reason to do this. So many things in the mathematics of conformal field theory have been done in genus 1, where you have these modularity properties of characters. And this gives beautiful, wonderful word, but we all know that this is not enough to characterize the theory. This is the point I would like to. So if you go to Eiger genus, okay, there is some idea about this. So this is just some, so I will not repeat exactly what is written there. But here you can, okay, in principle, heuristically, you can define this. One should say that recently there is hard stuff work by Kupiainen and other people to define something like this, although not strictly speaking conformal field theory, as far as I understand, because they work with these field theories where, for example, you have no vacuum. So it's something that, okay. What I should say that this kind of picture is also functional integral, heuristically, the starting point of what is called Segal CFT. It's more or less these Segal functors and coordinates starts as were defined started from a picture of this kind. This was just formally because then he wrote axioms compatible with this picture. Okay. Oh, the other point is this kind of stuff, as in genus 1, are expected to be related with, of course, the modular spaces in a broad sense of Riemann surfaces or Riemann curve, complex curve. When I say a conformal structure here, I mean a complex structure on a one-dimensional complex manifold. Okay. Okay. So one could think this as a function that depends only on class of the complex homomorphic structure on the complex manifold, but this is not the case, and this is related essentially to the fact that the unitary representation of the diffeomorphism group, or more general representation of the diffeomorphism group that appears in conformal field theory are projective, are not true representation, and there is some conformal anomaly, and then I have to have some care. There are clear abstraction to see this as functioning on moduli spaces, and one should look at this family. So you have, the idea is you have many function, one for each genus, but for a given genus, you have something which just depends, on some point in some space, which is not the modular space, but some covering, especially in this case, what is called the Teichmu modular space. In genus 1, this is the upper half plane in the complex plane. Okay. Okay, there is, yeah. So this is a long story. It's not my invention, and particularly was this important paper by Friedan and Schenker, where in a sense they said that, okay, conformal field theory, this should be intended two-dimensional, should be intended as a modular variant, which means in language modeled by Yasu, Megan, Longo, and Casini, and other guy that I don't remember the name. Benedetti, yes, Italian name. Yeah, it's not, okay. So this is related to sort of maximality. So you want something that you cannot extend in a reasonable way. And you need this. Since I don't work with this, because to construct this two-dimensional object is typically very difficult because you start. I want to work in the chiral setting. And in chiral setting, this maximality means that we are dealing with holomorphic vertex operator algebras, which means that the representation theory is trivial. So this is, so from the point of view of representation theory, this is not important, but this is not completely. Okay, so what is the point? Is that theoretically, even starting from this paper, one can guess some formulas that give you something that you skip the functional integral and just define some formal power series in the vertex operator algebra setting that should give these partition functions in principle, but they are defined independently. And more or less, maybe it's useful to give a very rough intuition because it's up here. So there is something like this. You can look at the torus, like this is a sphere. Then you make some tube here. Okay. And then you look at this tube. So this is not well. Okay. You shrink it to a point so that this glue together and this becomes a singular surface. And this is something which is related to cusps about. So we are going in the compactification of this. And in this limit, you have some special variables. So this is going to tend to something like this. It's very rough. So you have 2 points. Then you have a wire. It's intending that you glue this. Okay. And this is a limit. Essentially, this is more or less you have variable z and w, which describe this point, and then you have another which is going to, essentially the radius of this tube is going to 0. Say call this, I will call Q. And then you can do this kind of stuff in higher genus in various ways. Okay, so if you essentially have sort of perturbation of your, so power series expansion of these guys around this guy, you get something with that positive Q will be something like this. So the idea is that this gives you the partition function. This is very rough. And I hope it gives enough idea. I will not use this, so it's just to have an intuition. Okay. Just a few words about the terms. What is Teichmu? So this essentially is a covering. So you don't look at maybe, okay. No, I say what is Teichmu. So you take Riemann surfaces, okay. This is genus G. Typically, you have market points in order to do things correctly. I don't speak directly about this, but in any case, this space you have Riemann surfaces, so equivalence family of Riemann surfaces up to holomorphic isomorphism, but you need an additional structure. This is needed because if not, you get something wrong from the point of view of algebraic geometry. Don't so insist about this. So, for example, the upper half plane is I will say the moduli space is a covering of the moduli space of genus 1 curves. This is not correct because one should speak about elliptic curves. But this is special of low genus because you need to mark some points in order to avoid singularity. But please don't think about this, it's not so important because I'm going to speak essentially in higher genus. So you have this problem in genus 0 and genus 1. Higher genus you don't have. Okay. So what happens here? So you construct this space. This is done correctly. This was done by Teichmu. This is essentially a way to correctly define the moduli space. So you define this space. This space topologically is very nice. It's a ball in complex, some complex space. And then you have, okay, you have the mapping class group. I'm not defining what it is, but essentially you have this formula. What is the point? So here the diffeomorphisms are meant in the smooth real case. Okay, so you have a group of smooth diffeomorphism of X meant as a real smooth variety, and then you take the connected component of the identity here, and here you take orientation preserving. Then you make the quotient and you get a discrete group, and this is called the mapping class group. And this group is going to act naturally, I will not explain how, on the Teichmu space. And the idea is that, okay, the moduli space in a certain sense is this quotient. This is true as a set. From the point of view of algebraic geometry, you have to use stacks and things that are very nasty to understand from people like me. I've not really trained when I was young, this stuff. Okay, in any case.
What G equals
Roughly, so as a set, you have something like this. So this is good to understand what is happening.
G equals 1, the gamma G, which is the P is L2.
So when G, so I always put G. So this means typically you have to put MGN with n marked points. So this is for experts. So people that are more expert than me. In any case, typically you have this. And in order to define the stack, I think you have 2G minus 2 plus n should be greater than 0. So if G is equal to 2 or above, this is fine. You can take n equal to 0, and I take mg to be mg0. When G is equal to 1, you need one marked point. So actually what I wrote as M1 is M11. This is elliptic curves. And when n is equal to 0, you have to take 3, n equal to 3. So this is my convention. I don't need this because in any case, this stuff I asked to Giulio, the collaborator. Because without him, was impossible to do this stuff. Okay, in any case, so you have this. When you say stack, is simply that this group is not attacking in very nice ways, this group. So when you take the quotient, you get some singularity as an algebraic variety. This, I think, but in any case, so they have a complex structure. So it's not really algebraic, it's a complex variety with singularity. Okay, then there is a canonical here, I don't describe this, but it's quite natural. You can define a cocycle for this action, one cocycle. Okay, and using this one cocycle, you can define a modular form by this functional relation. Okay, this is a little bit, again, sloppy, because one would like that this form extend to compactification in a sense, and this is automatic when the genus is higher than 2, but in low genus, one should add extra conditions. If not, one get modular function, weakly modular forms, and so on. Okay. Right, this one. Okay, so when you were in genus 1, the cocycle is more or less given by this formula here. And then when get back, what is the notion of classical modular form? That's very important, and this corresponds to what you find for VOAs at genus 1. Okay. Oh, then I will need something more special than this is just to have right coordinates in a sense. So it's more usual in this setting, in contact with VOA, to use this another covering of the moduli space, which is called Schottky space. This is very nice space. I don't have very nice, but also very nasty, and depends on the point of view. Okay, say that this is another covering. It's less, in a sense, canonical than the Teichmu, but I will need this. In a sense, it's intermediate. So we have something like, so we can define maps. Okay. But then here I can define coordinates. Okay. So I can take the projective space, take one-dimensional complex, and I take the G power, and here I take the pointer at unit disk, again to the power G. Okay, this is clearly an honest complex manifold. Okay. And then you have an action of the group of Möbius transformations here, essentially by acting on each copy here, diagonally. And essentially, okay, of course, this is pure description since I did not say what exactly this set is. But there is such an open set, and you can define this Schottky space as a quotient, where this is SL2C, and before we had SL2Z, something. Okay. Again, we have this natural covering map. This is more or less what I wrote. And we have another, which is not really canonic, but more or less one can. There is a canonical way to fix it. And okay, so that if you make the composition, you get the projection of TG into the moduli space. And then I can define what is a modular function on, so a modular form, Teichmu modular form on the Schottky spaces and not on the Teichmu. That's the idea. Or maybe another important point is that another way to see these forms is to look at, these are not functions on the moduli spaces, but can be seen as sections of certain specific bundle, which is a line bundle, which is called the Hodge bundle. And you have this for every EG. Okay. And then I will use coordinates here because really I would like to define power series as I wrote here. Should be that these are small w, small z, and q. These are not exactly the same of the picture. There is some change of coordinate. I have to use something really specific. So I will use some coordinates and some open sets where things work and try to define functions here. Okay. Okay. Okay, nice. Start with the VOA. Now we'll define something, as I said, should be holomorphic, but many things can be defined in general, and then the result need holomorphic, but okay. So I take a VOA is something like this, is a vector space which is graded, and all these Vn, I'm not going to give a definition, but all these Vn are finite dimensional, complex vector space. And okay. You have these fields attached to vector in vector space. These are the vertex operators. Okay, and this is shooting this as a quantum field acting on V, which is the state space. Okay, I will. Okay. Okay. So this can interpret as quantum field. I will have a vacuum vector, and this zero order is just one dimensional, so it's the unique vector up to a constant in this V0. Okay, and the corresponding vertex operator is just identity. This is what I need to go further. Okay, then you have conformal symmetry, which is given by Virasoro. This I will not insist because we have seen something like this. The point that this energy operator, main point, this energy operator L0, come from this and is the one giving the grading of vertex operator algebra. And then I will need some property which are not universal, and this I want to assume, which are reasonable but not universal. V is simple. Typically, this is not true. And the other that it carries, and this is also a special property, a non-degenerate bilinear invariant. I will not explain this, but what I would say that, if, for example, if you have a unitary VOA, both properties are satisfied. Okay. Okay, VOA, so of course, VOA has a representation theory. We heard more or less about this during the workshop, and these are the things to find properly, not even so hard, but okay. But in any case, holomorphic, this is what I am interested in. Holomorphic means the representation theory is trivial. It is the category of vector, finite dimensional vector spaces, okay? In this case, the central charge, which comes from the Virasoro relation, is proved to be an integer multiple of 8. Okay, and then there is a famous example, which is the moonshine, which is in a sense the first VOA, because VOA were invented more or less to deal with this guy. And this is a special property that the V1, so V0 space is one dimensional, and when I ask that V1 space, so the first grid space, is 0 dimensional. And there is idea that this, essentially, these two properties fix uniquely this vertex operator algebra together with, but this is still big open problem in VOA theory. Okay. Okay, this is this conjecture by Frank. So this is a whole conjecture, but essentially by the guys who defined this VOA, but it's still open. Okay, let's go ahead. So maybe a minute that is more on the introduction. So there is a main point here. So just to give an idea where I'm going. So there are 2 points here. First point is say, okay, this higher genus partition function can be defined and give some very interesting invariant, which are much more strong than only genus 1. So we get much more information. And we would like that they have nice property from the geometric point of view, especially from the point of view of the geometry of modular spaces, so that they are Teichmu modular form. This is the point. And the second point is this, that was more or less conjecture by Frieda and Schenker, is that this family of all genus partition function determine the VOA. There are two points we are going to address. And the second one, you write something also in the paper by Siegel, who have an idea of this paper. So this means essentially this partition function is sort of like restricting the Siegel function to the surfaces without boundaries. And in this paper, Siegel write, okay, Friedan conjectured that this is enough to determine a theory. Okay, this he said this seems to be reasonable, but I don't know how to prove it. And actually, this is unproved, but in a sense, we will clarify in what sense could be so proved in special cases of VOAs. Okay. No. Fast here, because I want to define the partition function, VOA point of view. And okay, what I do, for each Vn, I fix the basis, which is orthonormal, say, but with this bilinear form. This bilinear form. Okay, satisfy this. And then I define this, say, what I can call a bilocal field. So has 2 points in localization. Okay. And then, okay, this is what you find in the literature. We just copy it, but well, that is related with this functional integral picture. We don't care about this. So we take this as a definition.
It does not depend on the basis.
This is clearly not depending on the basis. If you want, you can even take, without this, you have to take a dual basis on the other side. Easily seen that is independent of the basis because bases are related by orthogonal transformation. It is easily seen. So this is an invariant thing. It's a sort of Casimir, but in fact we got Casimir bilocal. Okay, and this is the definition. Oh, there are slightly different definition in the literature. I would say that this, exactly in this form, I found in a paper, first I think is Mason and Tuit in genus 2 cases. Then Gabardiel has something slightly different, Gabardiel with Volpato and others, which correspond in a sense to a different degeneration, a different way to expand, but should be equivalent. And okay, in other eigengenus, it appeared recently, for example, in papers by Tuit and Welby, where they do some computation, for example, for lattice. Okay, so this is something that the formal power series is completely fine. Okay. And of course, if we want to say something about these defined modular forms, we want to speak about convergence. And unfortunately, there is some convergent results, especially recently we used some papers by Bingui, because there is a problem of the sewing and factorization of conformal blocks. You have to use this kind of stuff. But at the end, we can manage to see that in a appropriate, which is the, I said before, I will use some open set. I don't want to describe, because something complicated is going to be around in order to define this set. But in any case, there is a set where, okay, this I can take to this series as a function. As a function which is analytic function of several complex variables. Oops. Yes. Okay. This is for every genus. Moreover, one can show something like this, that this function, so you have a natural action, as I say, on this Schottky space by SL2C, and you get this function is invariant. So you can look at this as a function of Schottky space. And a similar thing, so this is for holomorphic, but in a sense, here I want to take also the Heisenberg BOA, which is far from being holomorphic, but again, I can define the partition function. And again, you can show convergence in some way. We had a proof of this starting from the convergence of the other, because, okay, this is not exactly the stated. We have a statement that there is a function here is 1 over Cm to the power C. We just put we prove that there exists a function. And then we use computation in the lattice case by Twitt and Welby to identify this function with this formal power series here, inverse of this. And we can show they are the same. So I can formulate this in this way now, up to a constant. This is not really important. So the point is that, okay, take this series and we get this family of functions which are Teichmu modular form. One can, in a sense, one can look at the zoo result, genus 1, for holomorphic case, a special case of this. In a rather clear sense, of course, one has to understand why one has to put this guy here, but this is true because this is essentially the partition function, more or less, is the character. And the character is not modular form, it's a modular function, and in order to get a modular form, you have to divide by something, and it's the right thing to do. Okay. Okay. So this is the main, so what is, this is really actually hard stuff. And this is mainly due to Giulio. So there is hard stuff in order to prove that this is a Teichmu model form. because what you have to prove is modular invariance. So once you get a function here, you have to pull back to the Teichmu, look at the mapping class group and it acts and look at this invariant. And doing this directly is really hard. So the way it is done is using some sense the theory of conformal blocks. One can define bundles. So bundle of conformal blocks there. These are complex bundles. It's fine. And there is a theory which I don't understand, but Giulio seems to understand, which is called a Virasoro uniformization. And the point is that, so the main point is why holomorphic? Holomorphic means that these conformal blocks are one-line bundles first. And this uniformization is something that's related to the action of Virasoro. And when you look at VOA and how it works, look that this depends on the central charge. So the Müller model forms as a weight, and the weight here is C over 2, which is an integer because C is multiple of A. Okay. Okay, the way it proves essentially there is a way to say I have a line bundle on the compactification of the moduli space, and because conformal blocks can be extended to this compactification. And then there is something to say, okay, this bundle must be the Hodge bundle, which essentially means that we have a Teichmu modular form. So you have a sort of conformal, and this is a section on the conformal block. This is more or less the story. Don't ask me more because this is more or less all that I understand on this part. Okay. Okay, and now what we can do about this? So it is very well known that, for example, the genus 1, so the character of the moonshine is determined by the fact that this V1 space is equal to 0. Okay, and this is really some the theory of modular form in a more or less direct way. And I would like something similar. Okay, and okay. First of all, I have to speak of this, so we can look at the modular form as section of this bundle. Okay, and the point of this bundle, so look, so the modular group is not acting on the moduli space because the moduli space is quotient by this. When I pull back this bundle to the Teichmu, one gets a gamma bundle. So gamma is the modular group. So if you pull back a section from the moduli space, which is a quotient, you get an invariant section. And this is the relation. So, okay. Now, so I want to, and the point is that this is known various ways. Sometimes I have, as low genus, I have to make as a definition. In higher genus, this is a theorem. So this form extends to the compactification. This compactification, of course, is not really topological. It's something from algebraic geometry and was defined by Mumford and Deligne years ago. Okay, and yeah, there is this quantity is called the slope. I defined before. Lost with the slide.
On the previous one.
Yes, in fact. Okay, I define this quantity. So I take here a non-zero modular form, which is F. Okay, and I take the weight. Okay, it is integer. And then I look to the vanishing order, it could be 0, no, vanish, over the boundary of the compactification. Okay, of the boundary of mg into the compactification. Okay, this is a quantity that for some reason that I don't really understand is very interesting from people in algebraic geometry, especially for the geometry of the moduli space. Okay. And one take the inf of all this over all non-zero Teichmu for modular form of genus G. Okay, then there was this conjecture some years ago, Invenciones paper by Farkas and Popa. Again, I repeat, this is not so in Popa. And the conjecture is this, that this slope has a lower bound of this kind. So essentially, this is saying once fixed the weight, so Teichmu model form cannot vanish on the boundary too fast. Okay. Okay, this false. This was false some year. So this is, sorry, this is Harris Morrison, and few, so 15 years later, this was proved to be false. Okay. And there is a weak version, which is more or less due to Giulio, because it's not written explicitly in the literature, which SG is greater than 6, strictly. And this is open. People are working, some people are working on this. And this is known to be true if G is less than 12. And then why make this definition, this conjecture? Because we get this beautiful theorem that if we have that SG is greater than 1 for all G less than or equal to a fixed G over line G, then if we have a holomorphic VOA with C equal 24 and V1 equal to 0, then the partition function, if the partition function, then the partition function, genus G partition function of V is the same as the genus G partition function of the moonshine when the level, when the genus is less than this fixed genus for which the conjecture is true. Okay. In particular, if the weak slope conjecture is true, this is true for every genus, and this is what I write like what I call the partition function is just the collection of all genus G. Okay. Oh, essentially, the well-known fact that for genus 1, the character of the moonshine is universal, is fixed and related to the Klein J function is just a special case of this, because we know that this is true not only for G equal to 1, but for G less than 12. So we get many other consequences of this type. Okay. So what is the point here? If we have a slope conjecture, you say, okay, if it is true that the partition function determines the theory, so the VOA, at all genus, so if it is enough, strong enough invariant, then we have proved, for example, the uniqueness of the moonshine. But the point is this was conjectured by Friedel and Schenker, but we don't know why. So we try to understand in what sense, what kind of information gives the partition function on the VOA. And this is, we really have a complete characterization of this. And it goes as follows. So I take a family of vectors in the VOA that we call Casimir vectors. These, of course, are deeply related to these Casimir bilocal fields. And these vectors generate a subalgebra of the vertex operator algebra. It's clearly because of this Casimir form, these guys are all invariant under automorphisms of the vertex operator algebra. So this subalgebra, which I call partition function subalgebra, should be invariant under the automorphism group. And the theorem is the following. So I take two unitary VOA. Okay, we need unitarity at certain point. So before it was without unitarity. Here we have with some control. Especially the problem is that, for example, if you have a non-unitary algebra, vertex operator algebra, which is simple, and then you have no control on the simplicity of subalgebra, for example, or on the bilinear forms, on this is not nice, and this, when you have unitarity, you can control. So we assume unitarity. I would say, but maybe you have a counterexample. I don't know any example of non-unitary holomorphic VOA. You know? So, of course, the representation category of holomorphic VOA is unitary because it's trivial. So I don't know if this is related. In any case, most example we know, many interesting. So every example we know are unitary. Okay. So what is the theorem? Take two holomorphic VOA with the same partition function. Oh, it's easy to see that this is implies, for example, that the central charge are the same, the character is the same, so it's a lot of stuff. And then we say, what happens? So when it is true, and this is equivalent to this. So it is true that this implies the equivalence of the two. This we don't know, but this is exactly equivalent to this statement. So we have a unitary operator, just of vector space with the scalar product from V to U, which restricts to a isomorphism of this partition function subalgebras. This is the first term. And secondly, this intertwines essentially. So what is the meaning of this? So yeah, we have two subalgebras. PV is a subalgebra of V. PU is a subalgebra of U. V and U can be seen as PVU module and PU module. So the theorem say, okay, this partition subalgebra must be isomorphic, and its corresponding modules, given by U and V, must be isomorphic. So essentially, the problem of uniqueness becomes problem of uniqueness of VOA module. So one has a VOA module for a subalgebra and ask whether this has more structure vertex operator algebra. So this is solved in soft case, but so it's a similar problem in soft factor theory. You fix an endomorphism and you ask how many structure of Q systems it has. This is really the same case. The only difference is this is true also, for example, if the automorphic group of V or U is infinite, so these will not be rational, and this is not finite in a sense. But this is something clear. Okay. Almost finished here. So I go very rapid. No, maybe I've said something here. Okay, I said something. In any case, so what is the idea? So from the, I say two things rapidly, I'm sorry. Here is just that in homomorphic case, so they were classified when this V1 is non-zero, so the opposite side of the function. In all these cases, one can prove that the partition function determine the homomorphic theory. This has essentially been proved by Gabardiel and Volpato. We had to translate something. So this means that this module has a unique VOA structure, which is non-trivial at all. And we don't have an explanation for this, but this is true. Okay. And okay, now there is something that comes from corresponding with conformal net. I just would like to give an idea. So the idea is the following. From a conformal net picture, one imagine that if you take a special subalgebra, which is the fixed point subalgebra of the full automorphism group, V, seen as module for this, has a unique VOA structure. And this in a VOA community is known in very many special cases. For example, if the automorphism group is finite and the subalgebra is rational, the orbifold is rational, but you have to take assumptions. While for conformal nets, it's essentially always true. It's because of uniqueness of field algebra construction by Doppler and Roberts. Okay. There you can always take a compact group. And so one may hope that the explanation from this uniqueness is related to this kind of disease. Partition function algebra should be an orbifold. Okay. So for example, it's very well known this in VOA community that if this is finite and this is strongly rational, then by result of Kirillov and Ostrich, this has a unique haploid algebra structure, which means essentially that we have a unique VOA structure. Okay, so we say, okay, maybe something of this kind could be true for the moonshine. And we have some, I would say, weak empirical evidence. There are some computation by Dong Mason, by Hurley, which she was a student of Mason, and then Arada and Lang, another paper. Essentially, they studied this monster orbifold, which is this fixed point. and its primary fields. Okay, and then one can check, that's looking at tables, that the partition function of algebra of the moonshine agree with the monster orbifold up to a certain degree, and this degree is 24. This is not too much. But okay, we see, since it's very nice, we could conjecture that equality always hold. I guess it's, I don't know how to prove this equality. Maybe it is much more easy to disprove. Just to check with some computer. We did not try because I'm sure that it's true. In any case, if we assume this weak slope conjecture and this other conjecture, so a lot of conjecture, but what is nice is that they come from different fields. This is what I like. I'm not saying that this is a good strategy to prove this, but it's nice, it's something new. Okay, well, if you have this equality, and if moreover, and this is again an open conjecture, this should be rational, but no one to prove, and there is no way to prove, I think, this kind of things for a non-abelian simple group. So, but it's expected. So if this is rational and this is, then since the slope conjecture fix the partition functions, and here you have a group type extension, so the VOA structure of the extension is unique, then you get the uniqueness of the partition function. The uniqueness of the moonshine, essentially. So what I would like to say, okay, is this looks, oh, there are a lot of things inside. I'm assuming a lot of things with no control, but these are some of these things are interesting, for example, in other communities. So maybe we can learn something by other people. And the other thing to do is to say that, okay, there is people approaching to this uniqueness problem, but they are completely different way. So it could be useful to have some idea to think in a different. Okay, that's all. Sorry.
Question, comment?
Can you